In our Practice 1 video, we're going to be going over different calculations that we can perform that are related to our measures of central tendency and variability, as well as calculating z-scores for skewness and kurtosis, and finally using the IQR or the interquartile method to find outliers in a data set. We're going to start by going to our Practice 1 sheet in our Activity 2 spreadsheet. And we're just going to follow along with the processes and procedures that I give you so that we can calculate each of the following items I just listed off. Reminder that if you get stuck, you can always use the fx or the function icon in the formula bar to help search for functions that are included in Excel. This is more so helpful for you if you are going back through the activity and trying to do everything on your own without any supplemented help from myself in the video. So let's get started. In our Activity 2 data, for Practice 1, we can see that we've got some student IDs, mass, height, GPA, VO2, a bench 1RM, so their 1 rep max, measured in % of body weight. And then we also have a squat 1RM, also in % of body weight. VO2, I can add this here, is going to be milliliters of oxygen per kilogram per minute, just in case you wanted to note that. And yeah, so in this we've got our set of data. We've got quite a bit of values in this spreadsheet. And to the right you can see that I've created a table that outlines our measures of central tendency, variability, different measures or equations that we can use to evaluate distribution shape, as well as outliers using our interquartile method. We're going to start with our measures of central tendency and work our way down the table. Some of these we have done in a previous activity, so they might seem familiar. I've also done some of these in the practice problem videos, so if you've watched those, these will also seem a little bit familiar. So for mean, if you guys recall, our formula to find the average or the mean of data is to put equals average, and we put a parentheses, and then the number part in the syntax for the function is just to highlight the data that you want to find the mean for. So in this case, we can choose the first box or the first cell under mass. If you're on a Mac, you're going to hold Shift Command. If you're on a Windows computer, Shift Control, and then press the down arrow while you're holding those two keys. That will highlight the entire data set, or all the way down to the end of the data set, so that way you're not scrolling forever. And then you can press Enter, and you'll see that we have calculated a mean in this first box. Okay. We can then calculate the median. So equals, median has its own function in Excel, so we can type median, there it is. And then the same thing, we just select all of the data in the mass column. For the mode, we can't use, there actually is a function in Excel. If you start typing mode, there's 3 options: multiple, single, and just mode. This function would work for things like our bench and our squat data because they are whole numbers. Okay. However, when we're working with continuous data that has, decimal places, kind of an infinite number of values that could occur, we can't use this function. So we'll use the mode function for our bench 1RM and our squat 1RM values, but we're going to have to do an alternative method to find the mode for our continuous data that are in these 3 columns. So we'll save that for the end. But for now, I'll show you how the mode function works for the bench 1RM and the squat 1RM columns. So we can type equals mode. We just want to find a single mode. Okay, if you wanted to search this function in the formula builder, and we click on mode, it will show us that it returns a value, right, for the most frequently occurring number in an array or range of data. If we wanted to do the single, okay, it'll give us a single value, so pretty much mode and the mode single do the same thing. Either one of those would be suitable for this calculation. So we're just going to do equals mode, stick with that one, and then we can select our data and press enter, and we see that the most frequently occurring value is 133. We can then copy this across, and the mode would then be, the mode function would then be applied to our squat 1RM data. And I hadn't done this just quite yet, but we can do the same thing for our median and mean that we've already calculated. Because remember, as we copy across, the cell references for the columns will switch accordingly. So if I randomly clicked on this one, right, VO2 mean, I can see that all of my VO2 data has been selected. But again, for these ones, they're going to be special cases because we have continuous data, so we'll come back to those in a bit. For our measures of variability, we have variance, standard deviation, range, coefficient of variation, and our interquartile range. So we'll start with variance. For this one, the function is VAR, just var. Okay. Again, you'll notice that several options pop up. We're just going to do the compatibility function VAR. Again, this automatically translates to a sample calculation, so we don't have to worry about any degrees of freedom problems within Excel. So we do var, and then similarly to our measures of central tendency, hold Shift, Command, or Control and the down arrow, and we can highlight all of our data. Right? And then we can copy that function across to calculate the variance for every single one of our dependent variables. Standard deviation we've done before. It's STDEV, parentheses, and then the same process. We can highlight all of our data and copy the function across. For the range, this is the maximum value subtracted from the minimum value. We can always put multiple functions into one cell. So last week, you were able to find the maximum and the minimum using our search function. So we'll use the same functions that we identified last week. Max is for maximum. We type in max, and then we can highlight our data, add a parentheses, put a minus sign, so we're bringing your attention to the formula bar, type min, which will add our minimum function, and then we can highlight the exact same range of data. Put another parentheses and press enter, and we now have calculated our range for our mass data, which we then can copy across for the rest of our variables. For the coefficient of variation, our formula is standard deviation divided by the mean times 100 to make it a percentage. So what we can do is just press equals, insert the reference for our standard deviation, not subtract, divide by the mean that we've already calculated, and then multiply by 100. That will give us our coefficient of variation value as a percent, and we can copy that down for the rest of our data. For our interquartile range, we're going to be using, technically you can use two different functions. So I'll show you one function for quartile 3. I'll show you the other function for quartile 1. When we look at quartiles, we have 5 options or 5 quartiles in total. So 0, we don't usually count Q0, but that would be the minimum of the data set. Q4 would be the maximum of the data set. Q1 is at the 25th percentile, Q2 is at the 50th percentile, and Q3 is at the 75th percentile. So because quartiles are directly related to percentiles, there are 2 functions that we could use in Excel, one either in reference to the quartile, the second one in reference to the percentile value. So for Q3, we're going to use the quartile function first. Whichever function you want to use is completely up to you, or whichever one makes sense the most. We're going to choose the quartile INC function here. Our array in the syntax is going to be our range of data, so I'll choose my mass data. And then we're going to put a comma, and then you see we've been directed to a quart, right? So we either choose the minimum, maximum, right? We have 5 different options based on the quartile we're interested in finding. We are on the 3rd quartile, so we're just going to put 3, or you can click on this 3rd quartile option. That will add it to the function, and you can press enter. And we get the value in this mass data distribution that is at the 3rd quartile. Okay, so that's one way we can calculate Q3. The other way we can calculate a quartile is using the percentile function. So similar to the quartile, it's percentile INC. The array is going to be the range of data. And when we press a comma, it's going to give us a value or a variable k. K is going to represent the percentage or the percentile as a value from 0 to 1. So if we're at Q1, that is the 25th percentile, so we would put 0.25. Press enter, and we get our Q1 or 25th percentile value for each of our distributions for our data. To calculate the interquartile range, this is the difference between Q3 and Q1. So what we can do here is just put an equals Q3 minus Q1, enter, and we now have an interquartile range. Easy peasy. Moving on to our distribution shape. When we want to calculate sample skewness, this is the way that we can do it in Excel. We can also do this same function in SPSS, which we'll show at the end of this video, because we can do all of those calculations in one fell swoop. So sample skewness, there is a function in Excel, so you put equal skew, so easy to remember, and then you just insert your range of data you want to find the sample skewness for. Now, it's important to remember this is not the value that we use to investigate if we have a skewed sample or not, right? We have to convert our sample skewness into a z-score so that we can evaluate if we are in an acceptable range of skewness such that our sample is representative of a normal distribution versus not. So when we evaluate distribution shape using z-scores of skewness and kurtosis, the sample skewness and kurtosis are not the end values that you want to be looking at to justify if you think you have a normal distribution or not. Okay. What we need to do is calculate the z-score, which is sample skewness divided by the standard error. We can calculate standard error for skewness by doing equals, and the formula is the square root, so SQRT is the function in Excel for square root, parentheses, and it's 6 divided by the sample size. To find the sample size, we can use the count function that we used in activity 1. Remember, the count function will give us a number of all the cells that are in a given range that have values in them. So if we put count, parentheses, and then highlight our mass data, that count function will end up telling us the size of our sample. We then need double parentheses, so if you look up in this formula bar, you can see the black parentheses are paired and the red parentheses are paired. If you don't include that last parenthesis, it'll ask you or flash an error and ask if you want Excel to fix the problem for you. If you press OK, it'll automatically put the 2 parentheses, but just so we don't have people freaking out with error messages. Okay. So sample skewness, again, when we copy across, we can calculate the sample skewness for everybody, which ironically, they're all the same. Standard error. Okay. And then we can calculate the z-score for skewness by dividing our sample skewness by our standard error. And same thing, we can carry this across. For sample kurtosis, it's a very similar process. So we do equals, but instead of skew, we put kurt. And that will give us our sample kurtosis. We can look at our standard error of our kurtosis, which is going to be the square root of 24 divided by our sample size. So again, we're going to use the count function, highlight the data range of interest, double parentheses at the end, and press enter. For our z-kurt, it's the exact same process as our skewness, where we divide sample kurtosis by standard error. And then we can copy this function for all of our data. Okay. Remember that your evaluation criteria are going to be based on values between minus 1.96 standard deviations and plus 1.96 standard deviations. If you have any z-score values that are outside of those boundaries, then we can say that our sample is not normally distributed. Okay. For this data set, we can see, if we draw our attention to the z-skew and the z-kurt options, we can see that most of our values are pretty close to 0, right? With the exception, this is the highest value that we have, or sorry, negative 1.8 is the highest value we have, meaning that we've got a little bit of negative skewness in our height data. However, it's not outside, it's not less than negative 1.96, so we're still within an acceptable range. Thus, we can conclude that all of our variables, right, are relatively normal. Now, I also want to point out a note that we made in the lecture, that when you have a sample that is large enough, you don't necessarily need to test for normality in this way, because, right, if the sample is large enough, in our class we're saying that's at least 30 people, right? If our sample is large enough, then we can assume, based on the central limit theorem, that our sample should be normally distributed because we have collected a sample that's large enough to represent that normal distribution. Okay? So really, because this data set includes so many values, it wouldn't necessarily be pertinent that we calculate z-skew and z-curt values. However, this is a good example to show you that the central limit theorem does apply to this data. Okay. For outliers, using the IQR method, our formulas for this are going to be incorporating our Q3 and Q1 values, as well as our interquartile range. The lower bound is defined as Q1 minus 1.5 times the interquartile range. So Excel should pick up on order of operations, but I like to add extra parentheses just in case. Okay, and we can click our reference for our IQR, and that will give us the value that kind of sets the threshold for identifying outliers below the mean. To get a threshold for outliers above the mean, we can create an upper bound that's identified by Q3. So pretty much anything that's 1.5 times the interquartile range or the middle of our distribution. So Q3 plus 1.5 times the IQR. Press enter. Oh, whoops. This was a mistype. That was supposed to be parentheses. There we go. Press enter, and we get our upper bound. So once we have created these boundaries for all of our variables, we can use this fancy thing in Excel called conditional formatting to highlight these values. So one thing you could do is use a count if function if you just wanted to know how many outliers exist, right? You could say, I want to do a count if function for mass, and the criteria that I would be using is if values are less than my lower bound. Okay, so one way to identify them is by saying, do I have any outliers below? We could additionally copy this and say, instead of below, do I have any values greater than my upper bound value, which has already copied down. Okay. In this case, our count if scenario is showing that we have 0 outliers, right? But when we kind of pull this across, there's potential outliers that have been flagged in other variables. So what we can do to find these, right, we know that one exists, but we don't know which value is creating this flag here. So we can use conditional formatting in our height. So we highlight our entire column of data. And then up in the Home tab, you'll see a conditional formatting option. Go to Highlight Cell Rules. And because we've identified an outlier below the lower bound, we want to look for values that are less than our lower bound for height. So then we can choose this cell and then press OK. And then you'll see in this column, our outlier was identified, right? So the value that was less than 170 is 168.7. Not super alarming because it is pretty close to 170. Also, we only have one outlier, which can be expected based on our empirical rule, right? We know that there's a certain percentage of values that exist at various points of the distribution, with the majority or 95% of our values being between plus or minus 2 standard deviations. So if we have a single outlier that's still fairly close to the lower bound, we shouldn't be too concerned about it. But outliers are still good to identify just so that you know more about your data, right? So we could use this this process, right? If, let's say, we wanted to find highlight which outliers we had in our bench 1RM. Okay, so again, I can highlight my bench 1RM data. I do my conditional formatting, and in this case we have 2 outliers below the lower bound and 2 outliers above the upper bound. So I'll do my lower bound first, highlighting values that are less than my bench 1RM lower bound. And then I also want to add a rule that finds values that are greater than my bench 1RM upper bound. And now if we scroll through this list, we can see 1, 2, 3, and 4 values that have been identified as outliers. So you can feel free to find or apply this conditional formatting process to the squat and the GPA variables just for practice, more practice if you want it. For the last bit, you'll remember that we saved some mode calculations for our mass, height, GPA, and VO2 variables. So instead of calculating a singular mode, because we can't do that with this continuous data, we're going to do mode groups. So we'll just note that in the table, and then on your instructions page, I've given you a special cases area that tells you what the group range is, as well as the interval that you're going to be splitting the group up in. So you'll recall from last week, we created a grouped frequency distribution. Grouped frequency distributions are very helpful when we have continuous data, such as these examples. So for mass, we're going to be making a group range with a lower bound starting at 83 and our final upper bound ending at 82 with an interval of 1 kilogram. So let's do mass. We can identify a lower and upper bound column as well as a frequency column. And then we can create our table. So we have an interval of 1, so lower starting at 73. An interval of 1 would give us 74. And then 74 to 75. We now have a pattern that we can copy. There we go. And we're going all the way to 83. Or 82, actually. So I went 1 too far. Right, so then you can double check your range is appropriate, your interval is appropriate, and then we can calculate our frequency by using our countifs function. So we go equals countifs. Remember, countifs is where we insert 2 sets of criteria. So our first criteria range is just going to be our mass data. We can then put a comma. Our first criteria is going to be any values that are inclusive of the lower bound, right? Greater than or equal to, and our lower bound value of 73. We then insert our criteria range for our upper bound value. So it's going to be the exact same B2 to B101. And just a side note, I do want to copy this downwards. So I know as I copy down, my row references change. And I want to freeze my reference area to B2 to B101. So when I type this in, I'm just going to keep the $ B2 to B101. I can put a comma, and then insert my criteria for my upper bound, which should be exclusive, meaning that we're looking for values that are less than, not including, the upper bound. I then can copy this downwards. And in my final frequency grouping, I want to make sure that I include the final value just in case anybody has a mass of 82 kilograms. And then from here, our mode group we can identify as the group that has the highest frequency. In this case, we would say our mode group for mass is 78 to 79 because it had the most people in it. We'll do the same process for the other variables. So we also needed to calculate a mode group for height. I'm going to move this over. And you're basically constructing the same thing. Lower, upper frequency. We have a group range of 168 to 188 in centimeters with an interval of 2 centimeters. So lower bound starting at 168. Then we go 170. 170 to 172. Once we've identified a pattern, we can copy it until we get 188 at the bottom. And then you would go about doing your frequencies exactly the same. Okay. We can actually copy this function here and paste it since it's already constructed. From there, all we have to do is change the reference column. So instead of being at bench, we want it at height. But our reference values for our lower and upper bound should be the same. So from there, we can copy this downwards. And then just make sure that we are including the final boundary. And then we can identify our mode group based on the grouping that has the highest frequency. So in this case, our mode group for height would be 178 to 180. So for practice, you guys are going to do the GPA and the VO2 examples. Again, I've listed the group range and the interval for you, so you can construct your group frequency distribution table accordingly. And then you'll answer the questions on the answer sheet related to practice 1.